This is part 2 of a series on dropout. In this video, we will look at the second step of dropout, scale down, and scale up. This video was produced in Korean and translated into English. My voice is AI-generated text-to-speech. In the last video, we looked at zero out, the first step of dropout. In this video, we will look at the scale down performed in the prediction stage and the scale up performed in the training stage. Let's look at the optimal dropout rate and the relationship between dropout and regularization. Lastly, let's implement a neural network model with dropout applied using Keras Dropout class. Now, let's look at why scaling is needed in dropout and how it works. During training, some neurons in a layer are dropped out, and during prediction, all neurons are used, so the average output of the training and prediction processes do not match. So we need to adjust the average output. This can be done during training or during prediction. In the training stage, the outputs of that layer are scaled up, or in the prediction stage, the weights of that layer are scaled down. The example below shows how to scale down the weights during prediction. Let's call the probability of a neuron not being dropped P and assume it is 4/5. This is the retention probability. Then the probability of the neuron being dropped is 1 minus P, which is 1/5. This is the dropout probability, or dropout rate. Let's apply dropout to the hidden layer of this network. During training, the dropout rate is 1/5, so on average, 1 in 5 neurons is dropped per iteration. In other words, since the retention probability P is 4/5, 4 out of 5 neurons will remain without being dropped. And let's call the output of each neuron Hj. In this iteration, let's assume that the second neuron has been dropped. Then the output of this neural network will be like this. Let's assume there are no biases. And let's assume a linear activation function is used. There are 4 neurons left in the hidden layer, so only the outputs of those 4 neurons are used. However, during prediction, all 5 neurons in the hidden layer are used. Then, the output of the training process and the output of the prediction process will not match. One of the two needs to be modified. Here we will modify the output of the prediction process. We cannot match the two outputs exactly, but to roughly match the average outputs, we can multiply this result by 4/5. Then the average of the two outputs will be similar. 4/5 is the retention probability P. So using P, we can write this equation like this. In other words, W is reduced by P times. This is the scale down in the prediction process. Let's check this with a simple example. Let's assume we have a simple linear neural network as shown below. During training, dropout results in multiple subnetworks. Let's assume that all W's are 2, and the inputs are 1, 2, and 3. The retention probability P is 2/3. In the first model, the first neuron was dropped, so the output will be 10. In the second model, the second neuron has been dropped, and the output is 8. The output of the third model is 6. Then the average output is 8. Now let's calculate the output of this neural network during prediction. The prediction process uses an ensemble model that uses all neurons. If we calculate the output of this model using the equation on the left, we get 8. This is consistent with the average output of the subnetworks above. The paper proposing dropout explains scale down as follows. P is the retention probability. X is the output of the neuron. And W are weights. At training time, this unit is present with probability P and is connected to units in the next layer with weights W. At test time, the unit is always present and the weights are multiplied by P. The output at test time is same as the expected output at training time. This very simple approximate averaging method works well in practice. This is the scale-down method presented in the dropout paper. We can scale down the weights in the prediction stage, but we can also scale up the neuron's output in the training stage. They all have the same effect. The example below shows how to scale up the outputs of the hidden layer during training. Keras uses this method. Dropout probability and retention probability are the same as the previous page. The outputs of 4 neurons are used in the training stage, and the outputs of all 5 neurons are used in the prediction stage. Multiplying this result by 5/4 makes it the same as the result of the prediction stage. This is the reciprocal of the retention probability, 1 over P. Multiply H, the outputs of the hidden layer, by 1 over P. This is the scale-up process in the training stage. Or, if the dropout rate is R, it can also be written like this. If you apply scale-up in advance during training, you don't need to do anything during prediction. Let's take a look at the documentation of Keras Dropout. Here we specify R, the dropout rate. Inputs not set to 0 are scaled up by 1 over 1 minus rate, such that the sum over all inputs is unchanged. In Keras, dropout is used as follows. Here the word inputs refers to H1, which is the input of the dropout layer. So this means the output of the hidden layer. Next, let's experimentally check how much Keras Dropout applies scale-up during the training. Create a neural network model like the one on the right, and apply dropout to the hidden layer. Dropout rate is set to 0.5. Then 1 over 1 minus R becomes 2. Create and compile a model for training. And we create 2 additional models to check the outputs H1 and H2 of the hidden layer. H1 is the output before dropout, and H2 is the output after dropout. Fit this model to the data. Input data X into this model and check the outputs of H1 and H2. Dropout is applied in the training process, but the dropout is not applied in this step, because this is the prediction process. When checking H2, you can set the training argument to true to see the values with dropout applied. This applies dropout even at the prediction stage. Let's check the results. H1 is as follows, and H2 is as follows. The first and fourth neurons were dropped. This is that zero out is applied. And the output of the second and third neurons doubled. They were scaled up by 2. Let's run it one more time. This time, the second and third neurons were zeroed out, and the first and fourth neurons were scaled up by 2. Let's run it one more time. This time, 3 neurons were zeroed out, and 1 neuron was scaled up. The dropout rate of 0.5 is probabilistic, so it does not necessarily mean that 2 neurons will be dropped out. However, the scale-up still applies by a factor of 2. Let's run this code. The results are as follows. Next, let's look at the optimal dropout rate. In this paper, the dropout rate is mentioned as follows. Dropout rate is a hyperparameter. This controls the intensity of dropout. Typical values of P, retention probability for hidden units, are in the range 0.5 to 0.8. Please also note the following. Next, let's look at the relationship between dropout and regularization. Applying dropout is equivalent to applying regularization to a network without dropout. Let's look at what is mentioned in section 11.2 of this paper. Delta is a Bernoulli random variable, which is either 0 or 1. This means either dropped or not dropped. And P is the retention probability. This is the probability that the ith neuron's delta is 1. The expected value of delta is P, and the variance of delta is P times 1 minus P. Let's use the previous example again. This is one of the dropout models during training. The first neuron is dropped. So delta is 0, 1, and 1. Assume all weights W are 2. The input X are 1, 2, and 3. The probability P is 2/3. The output YD of this network can be expressed as follows, which is equal to 10. The prediction stage uses this ensemble model. All neurons are used and W becomes PW by scale down. The output YE of this network can be expressed as follows, which is equal to 8. Here D represents the dropout model and E represents the ensemble model. Now let's consider the loss L of the dropout model. This is a single linear model and uses a mean squared error loss. The gradient of loss LD with respect to WI is as follows. The loss LE of the ensemble model is also like this. The dropout model uses delta, and the ensemble model uses retention probability P. The gradient of loss LE with respect to WI is as follows. Now let's find the expected value of the gradient of LD. Since this gradient depends on delta, the expected value is as follows. Since the expected value of delta is P, it can be written as follows. These parts are the gradient of LE, so it can be written as follows. And since the variance of delta is P times 1 minus P, we can write this equation as follows. The right-hand side is equivalent to adding regularization term to the gradient of the ensemble loss. The expectation of the gradient with dropout becomes the gradient of the regularized ensemble loss. Therefore, the loss function can be written like this. This is the regularized loss for ensemble model. Finding the gradient of this loss with respect to Wi gives the equation above. This means that the loss of the neural network with dropout and the regularized loss of the neural network without dropout are the same. For this reason, dropout, like regularization, prevents overfitting. There is one more thing to mention. Among the weights in a neural network, some may contribute significantly to reducing loss, while others may not. During training, if all weights are updated together, the weights that reduce the loss significantly will continue to be updated a lot, while the weights that do not will continue to be updated little by little. This problem is called co-adaptation. Regularization doesn't solve this problem, but dropout does. This is because when dropout is applied, the weights are randomly selected and updated. And in this equation, this part corresponds to the regularization constant. You can see that this value is the largest when p is 0.5. That is, this value provides the highest level of regularization. Finally, let's implement a neural network with dropout using Keras. Since this is a code that we have used a lot before, let's just look at the dropout part. Add a dropout layer to the first hidden layer. The dropout rate is set to 0.5. And add dropout layers to the remaining hidden layers. No dropout applied to the output layer. During training, the dropout layer will perform zero out and scale up. Now let's fit this model to the training data. Let's check the result. If we don't apply dropout, we can see this overfitting. You can see that applying dropout prevents overfitting like this. Let's run this code. First, let's not apply dropout. You can set the dropout rate to 0. You can see that overfitting occurs like this. This time, let's set the dropout rate to 0.5. You can see that this prevents overfitting. So far, we have looked at dropout in neural networks in 2 videos.